All right, so chemistry of life. So chapter 2 covers basic chemistry. And I always ask the question, why would there be a chemistry chapter at the beginning of any biology type book? I think you all remember from Biology 103 you had chemistry in there as well, right? Maybe 2 or 3 chapters.
Because the backbone of every compound in the human body is carbon, so that the carbon backbone, you have to know, is the basis of the human body.
Good. So that's a very good point. And that's a big part of why that is that we have to cover chemistry in human anatomy and physiology, as well as when you take a biology course. First of all, biology has to do with what? Study of what? What is biology? Study of? No, biology. Life. Huh.
There's a lot of cells in biology 103.
So the definition of biology is what? Write that down and don't ever forget it. Biology is the study of life. So before we get into A and P, you have to understand life first. That's why you have biology first, before A and P. So when you think life, what's the first thing that comes to your mind? Cells. Should it be cells? The heart? Well, not trees are like living, right? Trees are life, but they don't particularly have a heart. But anything that is considered living is made up of cells. Okay? So cells are the basic unit of life, and we'll cover that in chapter 3. But when you look at cells, what are cells made of? Organelles. Good. What are organelles made of? Molecules. Good. You all remember the hierarchy. That's what we're going to go that path. Actually, you'll see the chapters go in that fashion. Chapter 2 is on chemistry, which is the molecules, the atoms. Then chapter 3 is on cells, and then chapter 4 is tissues. Chapter 5, you start getting into the organs and organ systems. So that's kind of how most anatomy books are arranged. But yes, so since cells are the basic unit of life, and we're talking about the human body, since the human body is living, it's made up of cells, which are made up of chemicals. And a lot of what goes on in the body is based on those chemicals reacting. So you do have to have somewhat of a foundation of the chemistry occurring in life. Okay, so some of the basics here. Chemistry is a science that deals with composition and properties of matter. So it's necessary to understand normal and abnormal functioning of the body. Biochemistry is the study of the molecules that compose living organisms. The organic molecules of life, as he mentioned. I want you all to highlight that as well. So the organic molecules of life there are 4 of them, and you all should remember those. Organic molecules of life. Carbohydrates, fats, proteins, and nucleic acids are the organic molecules of life, sometimes called macromolecules because they're pretty large molecules. Okay? Let you all finish writing. But you all do have access to this, right? Just so you know. Okay.
I'm not telling them that a blackboard. We just click.
Yeah, so when you go to Blackboard, click this course, and on the menu you'll see, I guess it would be PowerPoint. Yeah, under PowerPoint. Okay? Now, so what you'll realize really soon here is that for this class it's not enough just to memorize things. So organic molecules of life, instead of just memorizing that, I want you all to think about what that is. Why are we calling those organic molecules of life? Good.
Carbon
Well, let's start with the organic part first. Actually, we'll get to that later in this chapter. What is organic? Okay, that's the lay people's definition for organic. Natural, I think, is what I always hear. The real meaning of organic is really just what he said earlier. Molecules, chemicals that have a carbon backbone, a bunch of carbons with at least one hydrogen attached. And you'll see that later on in chapter 2. So organic molecules we'll define later, but they are molecules that contain carbon as the major element, primary element, with at least, so organic molecules have at least one carbon and one hydrogen attached to it. Okay? And anatomy, AMP. So that's the organic part. So carbohydrates, fats, proteins, and nucleic acids are chemicals, and their makeup is primarily carbon. They all have like a carbon backbone. Okay? So there's a lot of things that are organic. The gasoline you put in your car is organic, right? So when you think in natural, I guess it's natural. Bacon is organic. You don't think of bacon as organic, right? But yes, because bacon is made of what? Fats. Fats. Has like no carbs. It's very good. So pretty much, what did I do? Okay. All right. So the carbohydrates, fats, proteins, and nucleic acids. Now, where have you seen those before? Carbohydrates, lipids, proteins. Right, on food labels. Very good. So food labels tell you how many grams of carbs, proteins, lipids that you have in whatever that food is. But the part that's most important to me here is, why are these called molecules of life? Life.
Yeah, that happens.
Okay, so the foods we consume have these molecules. The real reason they're called molecules of life, though, is because that's what our cells are made of. Okay, so our cells are made of carbs, lipids, proteins, and nucleic acids. And cells are considered what? Life. The basic unit of life. If you all remember what a cell looks like? Describe it. Describe the parts, so to speak. Huh?
It's a plant cell, has a plant cell wall.
Good.
And it's got cell membrane.
Good. So stop there. So all cells have
Cell membrane.
cell membrane. What about cell wall?
No, just plant.
Do our cells have cell wall? So all cells have a membrane, a plasma membrane, cell membrane. Okay? And the cell membrane is made of, remember?
No. Is it cytoplasm? No.
Very good.
What is it?
Lipids. But it's a special word with lipids in it. Very good. So the cell membrane is made up of phospholipid bilayer. So there's the lipid. And if you also remember the picture of the cell, there were proteins embedded in the membrane, inside of the cell. And also the proteins and the lipids have carbohydrates attached to them. And we'll get to all that again in chapter 3. But so that gives you an idea of why these are called the molecules of life, because our cells are made of them, and cells are life. What about nucleic acids? You don't see that on your food panel. But where do you think those are in terms of cells?
Nucleic blocks of DNA or
So nucleic acids are the DNA and RNA. Anatomy and physiology? Yeah. Yes. So nucleic acids are DNA and RNA. Okay? And so the foods we eat, do the foods we eat then have nucleic acids? Think about the foods you eat. The foods we eat were once living, right? So that means their cells had DNA. So their cells have nucleic acids. Not sure why they don't put that on there. I guess it's not a major component in where we get the energy. So they just leave that out. But these are the molecules of life. And I just want you all to understand why they are called the molecules of life. Be familiar with those. Okay. And matter. So matter is anything that has mass and occupies space. All matter is composed of elements. And you all have seen a picture of the periodic table of the elements. Have you all seen this before? I'm sure. Okay, so what do you see on here? So these are all of the elements that occur in nature. And so basically everything in the universe is composed of one or more of these elements. So think of that when you see the word matter and you see the definition that matter is anything that has mass and occupies space, and that all matter is composed of elements, one or more elements of the elements combined. Okay, so anything that has mass and occupies space. Think that through for a moment. So that's pretty much everything. Okay, can you think of something that may not be matter? Air? That's what I always want to hear. Air does not matter? Air is matter, yes. Because air contains oxygen, nitrogen, and those have mass, even though it's very, very light. But we'll see in the, when you look at the periodic table, it gives you the atomic mass of each of the elements. So yes, air contains matter as well. All right, so the elements make up all matter, cannot be broken down by ordinary chemical means. Each has unique physical and chemical properties. So basically, just like we say, cells are the basic unit of life. Atoms and the elements that they make up are going to be the basic units of all things. Okay, so elements are the basic, and atoms are the basic unit of matter. There are 92 elements in nature, naturally occurring, and 24 of them have some biological role in the body. Identified by name, chemical symbols, or numbers. So you all should be somewhat familiar with the periodic table. You know, you don't have to memorize everything on there, but you should be able to tell when you see the periodic table what the numbers mean. Okay, so if you look at hydrogen, for example, and also what the letter it means. So when you look up there in the H, you see an H, you know H is what? Hydrogen. The symbol for hydrogen. Okay, and there are a few symbols that you all do need to know for the test, and I'll go over those in a moment. But the H is the symbol for hydrogen, and the 1 represents what? The 1 on the top? The atomic number. Very good. And then the number below?
mass number.
The mass number. Good. Atomic mass. Okay? So those are the things you need to be familiar with in terms of the periodic table. Okay, so the major elements found in the human body, you should be familiar with these: oxygen, carbon, hydrogen, and nitrogen. So these elements make up about 96% of the body by mass. And then there are other elements found within the body as well, and they have an important role, but they're found to a lesser extent. About 3.9%, those on the left there. And then there are trace elements, which make up less than 1/100th of a percent in the body. All right, so atoms. So what are atoms? So when you think of that word, basically you should be thinking what? So the smallest component of all matter, right? So living and non-living, very good. So atoms make up living things as well as non-living things. They are unique building blocks for each of the elements. Okay? Building blocks for each of the elements. Turn your phones off, please. And I forgot to turn mine off, so I can't fuss too much. Okay, so atoms and elements. So you get the relationship between atoms and elements. So when you look at that periodic table again, you see hydrogen. Hydrogen is hydrogen because of the atom hydrogen. So they're kind of the same thing. What makes hydrogen different from helium? That's probably a better way to explain it. Let's look back at that. So when you look at hydrogen versus helium, you'll see that hydrogen has an atomic number of 1. Helium has an atomic number of 2. Those two things, those mean something. So the atomic number of each element is different, right? The atomic number represents something about the atoms that make up these elements. Right? Anybody remember what that is? Excellent. Okay. So the atomic number represents the number of protons that there are in the atoms of those elements. So if you find an atom, and that atom has 2 protons, you know that that atom is which of the elements? Helium. Okay, so the number of protons lets you know which, let me pull that up here. I'm also doing this on integrity, so you all can look at it later. Just want to be in sync here. Okay, so y'all get that? So the number of protons will be different in each of the different elements. Okay, so it's the smallest component of matter, which cannot be broken down or changed by ordinary chemical or physical means. Okay, so basic unit of all things, living or non-living. All right, so all atoms are made up of subatomic particles. And those subatomic particles you all are familiar with, protons, neutrons, and electrons. So make sure you remember where they're found in the atom and also the charge that they have. So atoms of different elements contain different numbers of subatomic particles. That is what makes each of the elements different. And we just mentioned about protons. So in looking at the atomic structure of hydrogen versus helium, what do we notice? There's a different number of subatomic particles in each. So in hydrogen, so describe the hydrogen atom. Just look in there. So an atom of hydrogen, a typical atom of hydrogen, we know there are isotopes, which we'll get into. But a typical hydrogen atom will have how many protons? 1 proton. How many neutrons? None. And then how many electrons? 1. And that, of course, is if it's neutral. We'll get into that as well. So that's hydrogen. What about helium? So helium has how many protons? 2 protons. How many electrons? 2. And how many neutrons? 2. Okay? So it kind of follows a pattern there to some degree. And so what you all just told me is that the atomic number is determined by the number of protons in the atom. And the atomic mass, which is what you all said was that number on the bottom, below the name of the element, is atomic mass, and that equals protons plus neutrons. So your protons plus neutrons give you the atomic mass. So if I gave you a picture on the test, let's just go back for a moment, and let's just say I gave you a picture of the periodic table, and I just picked out beryllium, and I ask you, how many protons does beryllium have? What would you say? 4, right? Because the atomic number is 4. The atomic number gives you the number of protons. Okay? So what is the atomic mass of beryllium? Right, that number is given to you up here.
I couldn't see it going on.
Yeah, it's kind of hard to see from back there, but it's 9.128, whatever. Okay? So 9, you are just rounded. So the atomic mass of beryllium is 9. And then what is the number of neutrons found in beryllium? Good. So it's the difference
Just the difference from the protons.
from the atomic number and proton. I mean, the atomic mass and atomic number. So it's going to be 5. Right. Okay, let's go back to that. Just make sure you all are following me. So remember this equation here. The atomic mass equals what? Protons plus neutrons. So if you know any 2 of those, you can figure out the other. So by looking at the periodic table, that gives you the number of protons and the atomic mass. So all you have to do is subtract protons from atomic mass to figure out the number of neutrons. Okay? Y'all get it? Let's see if y'all can do another one. And let's see. Aluminum. So aluminum has an atomic mass of, and you can round that on to 27. So how many neutrons are in aluminum? 14. Good. Okay. And hydrogen? How many neutrons? 0. Okay. All right. Everybody have it? Okay. All right, so what is the atomic mass for each below? I think you all have that. The number of protons determine what element something is. Each element has a different number of protons. So one of the things that students get confused about is an element, an atom of an element can change in number of neutrons, right, or number of electrons. But one thing that stays constant is what? The number of protons. Okay, so link protons, number of protons, with each particular element. In other words, let's just say hydrogen somehow gained a proton, so it had 2 protons instead. If it has 2 protons, it's no longer what? Hydrogen. It will be helium. So keep in mind when we start talking about the subatomic particles being different, there's never a difference in the number of protons because that would make the entire element something else. Okay, so if the number of protons in an atom changes, it becomes a completely different element, and that doesn't usually happen. So atomic number is the number of protons. Atomic weight is the number of protons plus, actually should be mass, and the number of neutrons in an atom. Thus, atomic weight minus atomic number gives you the number of neutrons, as we just saw. Okay, so again, if I show you, and I may have a picture of a few of the elements like this on the test, so you should be able to tell me something based on what you see. Okay, so carbon has how many neutrons? 6, good. Okay, and one more, fluorine. A fluorine atom has how many neutrons? Okay, y'all have it. What about isotopes? So you should have an idea what isotopes are. So isotopes are atoms that vary in number of neutrons. So there are isotopes of each element. Okay, each element has more than one type of atom. And again, all of these are what element? Hydrogen. How do you know? Because they all have how many protons? 1. So all 3 of those are hydrogen. What makes them different is that they have a different number of what? Neutrons. Okay, so we say that these are isotopes of hydrogen. Okay, so they're all hydrogen. They act just the same. It's just the ones that have neutrons are a little bit heavier. Okay, so the hydrogen atom that has 1 neutron is called deuterium, and the one that has 2 neutrons is called tritium. Okay, so that's what we mean by isotopes. Atoms of the same element that have a different number of neutrons. And therefore, since they have a different number of neutrons, something else is different. The atomic mass, right? Because the atomic mass is determined by how many what there are. How many protons plus neutrons, right? So this one has only 1 subatomic particle in the nucleus. So it's not going to be as heavy or have as high an atomic mass as this one, which has 3 subatomic particles in the nucleus. Okay, so keep in mind that isotopes have different numbers of neutrons as well as a different atomic masses. And just a little bit of more information about isotopes, because you'll hear about them as you go on. Again, isotopes, since they are the same element, basically, they have the same chemical behavior. So all of those 3 isotopes of hydrogen will react the same way. So think of a chemical that has hydrogen in it. H2O, right? So you can make H2O out of any of those 3 isotopes. Okay, they're all going to form the same reaction with another hydrogen and oxygen. So they have the same chemical behavior, but different physical behavior, and that's because of the number of neutrons there. Okay, so what happens? So the more neutrons that you have, then the atom becomes unstable and starts to try to get rid of excess, and that is what causes decay. So the breakdown to a more stable isotope is what gives off radiation. So radioisotopes then are unstable isotopes that give off radiation. And every element has at least 1 radioisotope, and they can be detected with scanners. Radioactivity is radioisotopes decaying to stable isotopes releasing radiation. We are all mildly radioactive. So basically what's happening is the atom, the nucleus of the atom becomes unstable when you start to get a huge difference between the number of protons and neutrons in the nucleus. So they try to become stable by releasing some of the neutrons, and that gives off radiation, which can be detected in scanners. All right. So in terms of atoms, when you see the word neutral in terms of chemicals or atoms, what do you think? What are you thinking there?
No charge.
Hmm?
No charge.
No charge, no overall charge. Very good. So the atoms that you see in the periodic table are understood to be neutral atoms. Okay? And all that means is they have, so in order to be neutral and have no charge, well, we know that all of the atoms have subatomic particles that have charges, right? So protons have what type of charge? Positive. Neutrons have no charge. That's why they're called neutrons, neutral. And then electrons have a negative charge. So in order for sodium to be neutral, it has to have the same number of what? Positive and negative, which would be protons and electrons. Okay? So in order for sodium to be neutral, it must have an equal number of electrons as it has protons. Same for chlorine and all the rest of them. So since chlorine has 17 protons, for it to be neutral, it must have how many electrons? 17 electrons. Pretty straight there. Okay? And one other thing, so remember that you find the protons and neutrons in the nucleus of the atom, and the electrons occupy these electron shells on the outside of the nucleus there. Okay? And we'll see in a moment that the electrons fill the shells from the inside out. So, exactly. So since there are 11 protons, we said there has to be 11 electrons. So you put the first 2 electrons on the first shell. So the maximum that can go on the first shell is 2. And the second shell can hold how many? 8. Very good. And then if there is that you need to add, they have to go on the third shell, which also holds 8. Okay? Mm-hmm. Well, when you get out further, some of them will start holding 10 and 12, but for this class, 8 is the max. Okay, so valence electrons. You need to know what those are. So valence electrons, basically, really, you just have the electrons in the outer shell are given a special name called valence electrons. Yeah, so the valence electrons are just the electrons in that outer shell.
The first shell? Or
Outer, the outermost shell. So looking at the picture, sodium has how many valence electrons? 1 valence electron. Chlorine has how many valence electrons? 7 valence electrons. Okay? So you may see something like that on the test. I may ask about sodium, give you a picture there, and ask you how many electrons does sodium have. Sodium has how many electrons? 11. How many of those are valence electrons? Just 1. Okay? Now, the reason it's important to know about valence electrons is because they determine how chemicals react with each other. Okay? Now, they form bonds. You all heard of ionic bonds, covalent bonds. Well, nothing in the atom is regulating that except for those valence electrons. Okay? Now, let's see. There's something called the octet rule. You all heard of that? The octet rule states that all atoms are going to be unhappy unless their outer shell is full. Okay? All atoms are unhappy if they don't have a full number of electrons in their outermost shell. And in other words, except for the first shell, so remember the first shell can only hold how many electrons? 2. So the first shell, if the first shell has 2 electrons, then that atom is happy. Okay? If that first shell has 1, then the atom is not happy. So the atoms prefer to have a full outer shell of electrons. If we're talking about an atom that has a second shell, it's not going to be happy unless there are how many electrons? 8 electrons in that. There you go. Okay, so atoms with fewer than 8 valence electrons are unstable, and I like to say unhappy. Okay, so anything or anybody that is unhappy is trying to get happy. So let's look at what happens there then. So sodium, we just saw that sodium had how many electrons in its outer shell? 1 valence electron in its outer shell. So that means sodium here is what? Happy or not happy? Not happy. Not happy at all. And is chlorine happy? Nope. So neither of those has an outer shell that is full. Yeah. So they're just passing by, both unhappy. Wow, match made in heaven. So what is the best way for sodium to become happy? You may think by adding 7 electrons, but that's not going to happen. It's too hard. Right. So what you see here, the arrow, this means that that electron is going. And when it does, is sodium happy then? Yes. Why? Because it's full. Right, because that shell is not there anymore. And the second shell becomes the what? The outer shell. And that second shell is full. So in order for sodium to become happy, it gives away that electron. Now it's happy. Okay, what about chlorine? So first of all, sodium has to come across an atom that wants that electron. It's trying to give it away, but it needs takers. So chlorine comes around with that little gap there and wants to fill that gap to become happy itself. So chlorine does what? Accepts it. Okay, so now they're both happy. So now chlorine is going to have how many valence electrons? 8. Okay, so that's great. But now what happens to the overall charge of the atom? So now is sodium neutral? Is sodium still neutral? Remember what made sodium neutral was what? It had the same number of protons and electrons, but it just gave away an electron. So now it has 11 protons and only 10 electrons. So now it's a little bit more positive. So now we don't call sodium just the sodium atom anymore. We call it a sodium ion. So ions are formed whenever an atom either gains or loses electrons. Okay? Ions are formed when atoms gain or lose electrons. Now tell me what's going on here with chlorine. So chlorine becomes negative. So now, let's go all the way back. So originally, chlorine had 17 protons and 17 electrons, which made it neutral. Now it has gained an electron, so there's one more electron than there are protons. So now chlorine has an overall charge. So we don't call it chlorine anymore. We call it the chloride ion. Chloride ion, and it has a negative charge. So now anytime you see a symbol with a charge next to it, you know what happened to that atom. Gained or lost. Exactly. You should be able to tell me which happened to it. So if I give you something like potassium, you should be able to tell me potassium. The potassium atom lost an electron. Okay. So you'll see, you'll become familiar with those that are cations and those that are anions. Cations are ions that have a positive charge. You ever heard that before? Cations. So cations have a positive charge, and ions with a negative charge are called anions. Anions. All right, and I may as well go ahead and mention it here. What are ionic bonds? Right. So we'll get into covalent bonds later. But since we're here, this is the sodium and chloride are going to form an ionic bond. Now that one of the atoms is one of the atoms is positive and the other is negative, they attract each other and form a bond. Right? Positive and negative attract. To form sodium chloride, which is salt, table salt. Okay, so that's how sodium chloride is formed. Okay. So did y'all get that? So ionic bonds are formed when one atom gives off, first of all, that one atom has to give away an electron to the other atom, making one atom negative, the other one positive. And then they form a bond because they have opposite charges. And opposites attract. Very good. Okay. So basically, valence electrons determine whether chemicals react or not. Helium, for example, think about helium. So a neutral helium atom has how many electrons? 2. Right? Helium has 2 protons, so in order for it to be neutral, it must have 2 electrons. Now, so helium is happy, right? Neutral helium is happy. It's not going to give away or accept electrons because it's fine the way it is. So helium does not get involved in reactions, very many reactions at all. Okay, so the only way chemicals come together or atoms come together to form chemicals is because of the lack of stability or the lack of the full valence electrons, full number of valence electrons in the outer shell. Okay, so for all of those, we talked about carbon before, carbon being the major element found in what types of molecules? Organic molecules, good. And you can see, just looking at carbon right there, carbon, is carbon happy, neutral carbon? No. And so what it's going to do is form a bond. So this carbon can form a bond with 4 other molecules. I keep forgetting this is, yeah, it is, smart board. Okay. All right. So that's pretty much it there. And we just kind of talked about this. So ions and ionization. So that word ionization So you should, when you think ion, you should think of what just happened. Ionization. So one atom is losing an electron, another atom is gaining that electron. So that forms an ion, and ionization is just that, formation of ions by transferring of electrons from one atom to another to make the atom stable.
Is ionization the same thing as an ionic bond?
Well, ionization is the process of forming an ionic
Process
bond.
of giving or receiving.
Mm-hmm. So ionization is necessary in order to form the bond. Yeah. Okay. And okay, I didn't have to draw that on the board, write that on the board. So you have that here, anions and cations. So just remember that anions have a negative charge, and in order to become an anion, an atom must have what?
Negative charge.
And what must have happened to it? It must have gained an electron to become negative. Cations are positive because they what? Lost an electron. Okay? So put all those together. It's easy to forget if you all aren't going home studying this stuff. It makes sense today, but believe me, next week you'll forget it all. I am too. I'm surprised at most of you because most students don't remember this stuff. Okay, types of chemical bonds. So you all have heard of ionic bonds, covalent bonds, and hydrogen bonds. And you should know the difference between them. So we just went over ionic bonds. So ions are formed by transfer of valence electrons between atoms. And once they transfer electrons, the atoms become charged, and then those opposite charges attract, forming a bond. So the bond is formed by that attraction of positive to negative. Okay, so it's pretty much redundant. We just went over this, but just another view of it. So an electron is transferred from sodium to chloride in order to form the bond to make sodium chloride. Okay, so in step 2 it says sodium becomes a cation and the chlorine becomes an anion. In step 2, why does sodium become positive and chloride become negative?
Sodium lost electrons. Chlorine gained.
Right, good. You all are a pretty bright class. I'm proud of y'all. I usually have to go over this several times. All right, so there you go. And electrolytes, there's in 202 there's a whole chapter on electrolytes. So what are we talking about? So electrolytes are salts that ionize in water. So now you know what that ionized word means. That means they become ions by either losing or gaining electrons, and form solutions capable of conducting electrical current. Electrolyte importance. Why are they important? Yes, they're vital. In fact, we need them to survive. So they're important in chemical reactivity. In order for chemicals in our body to react the way they're supposed to, we need these electrolytes. They have an osmotic effect. You all remember osmosis. I think we talked about that last time. So they control the movement of water, and we'll talk more about that later on. And they also have an electrical effect on nerve and muscle tissue. So without electrolytes, our nervous system wouldn't work, our heart wouldn't work, our muscles wouldn't contract. So we need these electrolytes. And so what I want you all to think about when you see the word electrolyte, just think ions. So electrolytes are going to create charged particles. Okay, once they are combined with water. And just to let you know how important they are, imbalances in electrolytes have ranging effects from muscle cramps to brittle bones to coma to cardiac arrest. Okay, so we have to keep those electrolytes within balance. Free radicals are chemical particles with an odd number of electrons. So that right there tells you that the valence shell is not full in free radicals. They're produced by normal metabolic reactions, radiation, and chemicals. The problem is when you have these free radicals floating through the body, they cause tissue damage, and that's because they're trying to react. Like I said, the atoms are trying to become stable, so they destroy molecules by interacting with those molecules that they're not supposed to. So free radicals can cause cancer, death of heart tissue, and is also responsible for the processes that we see in aging. So to prevent having those adverse reactions within the body, vitamins should be taken. So one of the reasons to take vitamins is because they contain antioxidants which neutralize the free radicals within the body. Okay, and then there's a chemical called superoxide dismutase, which is produced in the body to naturally block free radicals. And then you can also take those vitamins to assist in that as well. Okay, so that is it for ionic bonds. Now, what do you all remember about covalent bonds?
And I when they're both charged the same, like I can't remember.
Well, so again, so when we say bonds, what are we talking about?
Together.
Right.
They have a double bond.
So yeah, with covalent bonds, there are double covalent bonds and triple.
Well, I was thinking of that.
But just when we say bonding, that just means two atoms coming together. Okay? Sort of like they're holding hands. So they become one to make of some chemical. Okay, so they're formed by two atoms sharing valence electrons. So how is that different from electrons? Just looking at that first sentence at the top. So just formed by two atoms sharing
Same amount of electrons?
valence electrons. The key word is sharing. In ionic bonds, right. So in the ionic bonds, one atom donated one to the other. So you could say formed by two, the atoms transferring, one atom transferring electrons to the other. Here, both atoms keep their own electrons. They just share part-time with the other atom. Okay? So y'all get it? Formed by the sharing of the electrons versus the transfer of electrons. So those are the key words there. So the types of covalent bonds that there are single, double, and there are also triple covalent bonds, which are rare, but they do exist. And then there's nonpolar versus polar covalent. Remember those? So what was the difference between polar covalent and nonpolar covalent? Not charge. So with covalent bonds, we don't really think of charge. There is a partial charge with one of the types. But which type? So with polar covalent, so the key word here is in nonpolar covalent bonds, the sharing of electrons is fairly equal. And what do we mean by that?
They share the same amount of electrons?
Yeah, well, they share the same amount, but the electrons spend the same amount of time on each. Okay? Whereas polar covalent bonds, there's unequal sharing of electrons. And let's see if we can find a picture to help illustrate that. So this is actually an example of the formation of a non-polar covalent bond. So then you have 4 covalent bonds formed here. So remember we said carbon had 4 valence electrons. That means carbon is looking to become stable by not giving away or receiving, but sharing electrons with other atoms. So this carbon is able to share the 1 electron that hydrogen has here, and it does it 4 times. So now carbon feels like it has what? 8 electrons. Okay, so it's happy. So it doesn't have all 8 to itself, but at least it feels like there are 8 electrons in its outer shell. And each hydrogen is benefiting as well. How? So, exactly. So hydrogen has how many electrons by itself? 1. So it's looking to share an electron with carbon or whatever else is in the way. And exactly. So now hydrogen feels like it has 2 electrons. Okay? So that is a covalent bond. Covalent bonds form when 2 atoms share electrons. And that is CH4, which is methane gas. So that is an organic molecule. That one is nonpolar because the covalent bonds involve an equal sharing of electrons. And it makes more sense when I show you unequal sharing. So this is also equal sharing. And equal. Let's get to an unequal sharing. Okay? In polar covalent bonds, that's where you have unequal sharing of electrons. Okay? So again, remember each hydrogen atom is sharing its 1 electron with oxygen there. Okay? And by the way, oxygen has 6 valence electrons. So oxygen wants to gain what? 2. So what it does is forms a bond with 2 hydrogens, and those 2 hydrogens provided with those 2 electrons that it needs. The difference is the electrons are going to spend more time with 1, either on the hydrogen or the oxygen. And what happens is the 2 atoms of hydrogen, they have their electron, but the electrons there spend more time with oxygen than they do with hydrogen. So it's unequal sharing. So even though all of the electrons are going around the hydrogens and oxygen, those electrons spend more time around oxygen.
How can you know?
Well, you don't know by looking at it. The reason why, though, is because of the. If you think about electrons, what would attract electrons? Protons. So which one has more protons? Oxygen. That's right.
Oh, so if it has more oxygen, more than likely it's going to be a polar.
Exactly.
I mean, if it has more oxygen, if it has more protons.
Right.
It's
So
more
that's
likely to be
that's
polar.
the major factor. Okay. Good question. So.
If there was a hydrogen connected to each electron, there was like an electron from the hydrogen connected to each electron from oxygen, then it would be not polar.
Wait, I'm not sure what you're saying.
You said there's 6 electrons on the outer shell of oxygen, right?
Right.
If there was a hydrogen connected to each one, no, that's not
Yeah. Yeah. What you're thinking about
That would be
is
more than X.
right what it doesn't have. So oxygen is lacking those 2. So it's trying to share in order to get those 2. and it's sharing, the hydrogens are sharing to get 2 electrons in its outer shell. Okay? And really the periodic table is set up so that people who are in chemistry, if you don't have to take chemistry, you will learn about that. You just know which atoms are going to form ionic bonds, and which ones are going to form covalent bonds. Okay? There's something called electronegativity. Yeah. So there's a pattern to how the periodic table is set up. It's pretty fascinating.
So hydrogen is one, but it can share more.
Hydrogen has 1 electron. It can only share that one. But when it's sharing that one, it's also receiving, right, a sharing
I
partner.
still don't understand what makes it
What?
positive of the proton.
No, what makes it polar is that the electrons just spend more time around oxygen than they do around hydrogen.
Because
Okay.
it has more protons, the electrons.
Right, there's a stronger pull for those electrons to come toward oxygen because oxygen has more protons. Hydrogen only has 1 proton pulling at the electron. You don't have to know that. I mean, if it helps for you to know that, yeah. You get it? So if you look at, it would be easier if we had a picture of an atom of oxygen. You can see that inside the oxygen there are 8 protons versus, just think about it. If I have 8 protons here and 1 proton here,
You got 8
electrons in the middle, where are the electrons going to go? Where I have more protons. And that's what it is. So right, it's like a tug of war sort of. Okay? So that's what's happening. Now, since the electrons are spending more time with the oxygen has a partial negative charge. It kind of feels like it's a charge. It kind of feel like it's an ion, but it's not a complete ion. So that symbol just means partial negative. So anytime you have a polar covalent bond, that molecule is going to have a negative end and a positive end. So with water is polar, and the reason water has the properties that it does is because of its polarity. So in a water molecule, the oxygen has a partial negative, and the hydrogens have a partial positive charge. Do you all remember the properties of water at all?
It's soluble.
Solubility, right, that's one of them. Adhesive, cohesive, high surface tension. I think that should come up later on. Okay, and then hydrogen bonds. Hydrogen bonds occur when there's attraction between a slightly positive hydrogen atom in one molecule and a slightly negative oxygen or nitrogen atom in another. So looking at water, water has hydrogen bonds, and let's see what those look like. So if you look at the picture here, so what type of bond is this? So you have oxygen here and 2 hydrogens. What type of bond is this? So I didn't even touch it. So the bond between the oxygen and hydrogen is, as you all said, covalent. Okay, polar covalent. But the bond between 2 separate water molecules is a hydrogen bond. Okay, so what is a hydrogen bond? Hydrogen bonds occur when the partial positive hydrogen in water forms a bond with the partial negative oxygen on another molecule of water, for example. Okay? So the molecules of water stick together because of those hydrogen bonds. So just keep in mind, water, the glass of water, their bottle of water, there are trillions and trillions and trillions water molecules, and they are sticking together by hydrogen bonds. Each individual water molecule is held together by what? Covalent bonds. So keep that in mind. Now, and then I'll let you all go after this. So why are covalent bonds, or why is polar covalent bonding that we find in water so important? It gives water its properties. If water didn't have polar covalent bonds, we couldn't exist as we do. So a lot of the activity that goes on in our body is due to what? Water. So the reactions that water undergoes is going to be due to the polar covalent nature of water. So the most important inorganic compounds in living organisms occur because of the properties of water. So account for its ability to support life. Solvency, remember that? So when you take medications, for example, they have to be able to dissolve, right? Dissolve in water. So if water wasn't nonpolar, some of those chemicals would not be able to dissolve. Okay? So solvency, cohesion, adhesion. What's the difference between those? Cohesion and adhesion. Cohesion probably means stick together, right? So water molecules stick together. Okay? Water molecules stick together because of hydrogen bonding. Adhesion means they stick to something else. So even if that bottle of water is empty, I bet you can find a drop somewhere where that a drop of water is sticking to the side of the container. Okay? That is because of cohesion. And cohesion is also the reason for water having a high surface tension. And look at this. How is it that this little insect can sit on top of the water without going through? High surface tension. So that just means on the surface of water, the molecules seem to stick together even stronger through hydrogen bonding. What's wrong?
I was trying to think of that hydrophobic and stuff because of the cell. That's what I was.
Yeah, so you have hydrophobic and hydrophilic parts, and that comes into this as well. But you know, if someone jumps off a bridge, they can hit the water, break their neck, right? Break bones in their body, and that's because of high surface tension. So it basically right. So the water molecules on the surface don't want to separate. So it takes a little bit more, and that's also why you can skip a rock on top of water because of its high surface tension. So now you know that the surface tension is due to what? What type of bonds? Hydrogen bonds. Good. All right, we'll stop there. Now, so